Hey everybody, welcome to the EM370SI online final couple of videos. We're going to be working on open channel flow problems here just to wrap up preparation for the final. Let's get into it. All right, so we have the flow rate in a clay line channel n equals 0.025 shown in the figure below is said to be 300 feet cubed per second. To prevent erosion on the sides, velocity must not exceed 5 feet per second. For this maximum velocity, determine the width of the bottom B and the slope S sub O. All right. So, what we're going to get started with here, just write out what we know real quick. Then we'll move on from there. All right, and then we're looking for B and SO. Cool. So we can find B using our continuity equation. Velocity equals flow rate over area, because we know the velocity and we know our flow rate, and then we can calculate this area here. So this area, I'm going to call this L1. This is my L2. So L1, we know this, so we look at it like a triangle. This side is 2 feet, and then we know the angle there. So L1 is just 2 over tangent of 30. Similarly with L2, it's 2 over tangent of 45. Giving us L1 is equal to 3.46, and L2 is just 2, right? Because it's a 45. It's an equilateral triangle, so that makes sense. All right, so let me start that off a little bit. So we have, so this is a trapezoid, right? So the area of a trapezoid is 1/2 times this side plus this side multiplied by the height. You could do that, or you could just get the area of composite of the triangle, rectangle, and the other triangle. But we'll just do this real quick. So B, this side, plus this side up here, which is L1 plus B plus L2. And then we multiply that by the height of 2. And then that is all under our flow rate of 300. So using this relationship here, we can solve for our B value, which will be 27.3 feet. So needless to say, this isn't exactly drawn to scale, but that's our B value. All right. So now that we know all the geometry of our channel and some other characteristics about it, we can use this open channel flow equation. So V equals kappa over the Manning coefficient, hydraulic radius, 2/3, or no, wait, that's not the name of that. Wedge parameter, something like that. Anyway, multiplied by SO to the 1/2. So kappa here we're going to say is 1.49. That's not always the case. Sometimes we'll just say 1 or something like that. And we're given that n is 0.025. Other things we know, RH is just the area over the wetted perimeter. So the area that we calculated up here, or we'll just plug values in of that, no, sorry, 1/2 times 27.3 plus 3.46 plus 27.3 plus 2 times 2 over the perimeter, which is just the wetted perimeter. So it's not the entire thing. It's just boom, boom, boom. So that's going to be 27.3 plus 2 over sine of 30. Right, that's going to be this length here. And then 2 over sine of 45, which is this length there. And this gets us 60 over 34.1, which is 1.76. That's supposed to be an H. There we go. And then we can calculate our slope now by plugging in all this stuff that we know. So maximum velocity, 5. Kappa, 1.49. Manning coefficient, 0.025. R sub h, 1.76 to the 2/3. And then our slope that we're going to solve for to the 1/2. So divide all this stuff over, square it, and you'll get your slope is 0.00331. And our units on that are going to be, right, just feet per feet, because we're working in feet over here, so that's what's going to come out to be. All right. So you won't see anything a whole lot more complicated than this for the final. There's another video that I'm gonna put up after this one for another open channel flow problem. So watch that one as well, and then yeah, let me know if you have any questions.